Understanding phase velocity and group velocity is important in RF and microwave engineering. It also helps understand how energy and information move through the universe. 1. Phase velocity, VP, the speed of a ripple. Imagine you drop a stone into a perfectly calm pond. You focus your eyes on one specific crest of one specific ripple, and you track how fast that single crest moves outward. That is the phase velocity. In a pure, continuous sine wave, the wave extends to infinity in both directions. The mathematical expression for the voltage or electric field of a single traveling wave is shown here, where V0 is the amplitude, omega is the angular frequency, beta is the phase constant, how many radians of phase shift occur per meter. Omega t minus beta z is the phase of the wave. To track a single crest, you are looking for a point where the phase remains constant. If you take the derivative of the phase with respect to time and set it to 0, you get the speed of that constant phase point. Vp equals omega over beta. The catch: a perfect infinite sine wave cannot carry any information. You can't use it to send a voice signal or a digital 1 or 0 because it never changes. It has been oscillating forever and will oscillate forever. To send information, you have to turn the wave on and off or modulate it.
2. Group velocity, Vg, the speed of the package. The moment you turn a wave on and off or modulate its amplitude to create a pulse, you no longer have a single frequency. According to Fourier analysis, creating a pulse requires adding together multiple continuous sine waves of slightly different frequencies. When you add waves of slightly different frequencies, omega 1 and omega 2, and slightly different phase constants, beta 1 and beta 2, they interfere with each other. In some places, they add together, constructive interference, and in other places, they cancel out, destructive interference. This interference creates an envelope or a wave packet. The rapidly oscillating ripples inside the packet move at the phase velocity, Vp. The overall envelope, the packet itself, moves at the group velocity, Vg.
The formula for group velocity is the derivative of frequency with respect to the phase constant. Vg equals d omega over d beta. The rapidly oscillating ripples inside the packet move at the phase velocity, Vp. The overall envelope, the packet itself, moves at the group velocity, Vg. 3. Dispersion and energy transfer, the crux of the matter. Why do we care about the difference between the two? Because energy and information exclusively travel at the group velocity. In a perfect vacuum, electromagnetic waves of all frequencies travel at the exact same speed, the speed of light, c. In a vacuum, Vp equals Vg equals c. The wave packet and the ripples inside it move together in perfect lockstep. However, almost everything we use in microwave engineering, dielectric PCB substrates, coaxial cables, and especially waveguides, is a dispersive medium. In a dispersive medium, beta does not scale perfectly linearly with omega. This means waves of different frequencies travel at slightly different speeds. When your pulse, which is made of multiple frequencies, travels through a dispersive medium, 3 wild things happen. The speeds decouple. The phase velocity, Vp, and group velocity, Vg, are no longer equal. The conveyor belt effect. If Vp is greater than Vg, you will actually see the high-frequency ripples form at the back end of the wave packet, travel forward through the envelope, and disappear at the front of the packet. The envelope itself is plodding along at a slower speed, carrying the actual energy. Breaking the speed of light. In devices like hollow metal waveguides, the phase velocity, Vp, actually exceeds the speed of light in a vacuum, c. This does not violate Einstein's theory of relativity because phase velocity carries 0 energy and 0 information. The group velocity, Vg, which carries the actual radar pulse or data stream, always remains strictly slower than c. When a signal is sent through a highly dispersive medium, like a long run of waveguide, the different frequencies making up the pulse travel at slightly different speeds. Over a long distance, the wave packet spreads out and flattens, a phenomenon called group delay dispersion. If you are sending high-speed digital data, these smeared pulses will eventually overlap, corrupting the data entirely. Enjoying this? Smash that like button and subscribe for more RF and microwave engineering content. Drop a comment below with what you want to see next. I'm reading every single one. Let's get back to it. Thank you.